Hello, my name is Lester Paggio, and I chose the topic of Large Hadron Collider. So, what is it? In its simplest terms, it is a large colliders of hadrons, but in terms of the whole thing, it is the most powerful particle accelerator that operates on energy that is 7 times higher than any powerful previous machines, and it produces approximately 600 million collisions per second and delivers an incredibly high amount of energy. It is located at CERN Laboratory near Geneva in Switzerland, and CERN is the largest laboratory and it is dedicated to the pursuit of fundamental science. In terms of its size, it weighs 38,000 tons and runs for 27 kilometers in a circular tunnel 100 meters beneath the ground located between France and Switzerland. And the collider itself is, is not only part of the LHC project, and there are two other essential parts of the project, which includes the detectors, which are the Atlas, ALICE, CMS, and LHCb, and Worldwide LHC Computing Grid, which is a global network of computers and software that is essential to processing the masses of data recorded by all of the LHC detectors. So, what is the purpose of building the Large Hadron Collider? Scientists and researchers wanted to increase our knowledge about the universe by building the Large Hadron Collider, since it could enable scientists to make new discoveries, which then, when applied, will profit us. In 1977, history has it that Sir John Adams proposed the creation of an underground tunnel. He believed such a powerful particle accelerator will one day be built and would possess extraordinary energy, and he was right. They discovered the Higgs boson during the compact muon solenoid experiment, which contains a mass that is about 126 gigaelectron volts. This discovery has opened a new chapter with regards to research bordering on the universe's stability. Standard model. Scientists propose a standard model in which it tries to define and explain the fundamental particles that will make the universe what it is. It combines elements from Einstein's theory of relativity with quantum theory, and it also deals 3 of the 4 basic forces of the universe: strong nuclear force, weak nuclear force, and electromagnetic force. The fourth one, which is the gravity, it does not address at all. Collisions of protons in a Large Hadron Collider. So what does it look like inside in the collider itself? So first, the two beams are fired along 2 pathways, one going clockwise and the other going counterclockwise. And both beams are accelerated to near the speed of light. And the last step is both beams direct towards each other and they just record what happens in there. So why is the Large Hadron Collider one of the greatest breakthroughs of all time? Again, the LHC gives us the next huge step as to how the universe works and structured. As I mentioned before, scientists and researchers and physicists, they are working to extend their knowledge as to what the universe is about. They want to know more about what is out there by asking simplest questions, which could be very difficult to answer. Furthermore, in the standard model, one of the things that they want to figure out is the Higgs boson particle, which could answer questions about the mass, matter, antimatter, and dark matter. Supersymmetry. The standard model classifies particles as either fermions or bosons, depending on the property known as spins, which can be thought of as the rotation of the system around its axis. Supersymmetry predicts that each fermion or boson in the standard model has a superpartner with a spin that differs by half of a unit. That is, bosons are accompanied by superpartner fermions and vice versa. If this is true, it would remove certain runaway infinite quantities that crop up in the mathematics by letting corresponding particles cancel out, and it would make room for gravity because fermion-boson and boson-fermion conversions might involve gravitons, the long-theorized gravity force carriers. And the idea of the Large Hadron Collider can be used for the practical applications. Technology found that in particle accelerators is already used for certain types of cancer surgery, and CERN gave birth to the World Wide Web because scientists needed a way to share that massive amount of data they were collecting with each other. So in these 2 photos that were shown in here, it shows the interaction of the standard model and quarks. The first one is just more complicated, but the second one gives us a simplified version of it, simplified version of the Higgs boson. So, what are the discoveries that lies within the Large Hadron Collider? Obviously, the first one is the Higgs boson particle. We already explained it so much about this, but this is still very important and the most significant discovery in the Large Hadron Collider because it created many questions that we have never thought regarding the structure of the universe. The second discovery is the tetraquarks. In 2003, researchers in Japan found a strange particle, X3872, an anticharm, and at least two other quarks. While exploring the particle's possible existence, researchers found Z4430. The LHC has since discovered evidence for several such particles which break or at least substantially bend the established model for quark arrangements. Such Z particles are fleeting but may have thrived for a microsecond or so following the Big Bang. There are some discoveries, but it still remains hypothetical since there are not enough evidence to theorize these events. We have already discussed the supersymmetry, but we still haven't discussed about coordinated motion. One theory advanced to explain the phenomenon says that the impact created an exotic state of matter called quark-gluon plasma, or QGP, which flowed like liquid and produced coordinated particles as it cooled. Although most physicists favor this idea despite its problems, some have argued for a second explanation involving theoretical field created by gluons, the particle that mediates strong force and pays quarks and antiquarks into protons and neutrons. This hypothesis says that gluons zipping along near the light speed formed fields that cause them to interact. If this is correct, this model could provide valuable insights into proton structure and interaction. Scientists working on CMS and ATLAS detectors at the Large Hadron Collider reported the Higgs boson decaying into two muons for the first time. So this happened recently this year. These fundamental particles are like electrons, but are classified as a second generation particle, which decay quickly and are not present in normal matter. They decay into a pair of muons only occur for 1 in every 5,000 Higgs boson produced. This rare phenomenon has been difficult to detect as muons are relatively light, meaning they interact weakly with the Higgs bosons. So these discoveries and questions that are created that lies within the LHC makes the LHC to be one of the greatest breakthroughs of all time. These discoveries made everyone that are involved in this project to cooperate each other to find answers that were never thought of before. Because of this creation, we became more curious as to how the universe works, and it is seriously the next huge step to know what's out there. So, which is cool. And these are my references.